Hi. The chapter 2 that I would like to discuss estimation problems. So one common problem is linearly separable case for logistic regression. So this is the subset of iris data in R. The iris data have 150 observations and 50 observations each for 3 species. And this actually takes only just first 2 groups. The first one is the Setosa. This is a species of iris. And the second one is versicolor. So we just drop the last one called Virginica. So just we close out this and we use the first 2 groups. So the Setosa is 0 and versicolor is 1. And actually, if we see sepal lengths here and sepal widths, these 2 groups are separable in the sense that one straight line perfectly separate these into 2 groups. And actually, there are multiple possible lines to separate it. For example, if we think about this line, it can perfectly separate the black group. This is Setosa and the versicolor, the red triangles. But also, you can see that another line can separate 2 groups perfectly. So there is no unique solution to separate these 2 curves. Basically, logistic regression is fitting the probability curve perpendicular to the separation line. So this is the probability, and yeah, so think about this is probability and probability of being versicolor. Then fitted curve will be like this. So if we don't have unique line which separates these 2 groups, then we cannot really uniquely determine the logistic regression parameters. And another problem happens. So this is also not even unique, but also the beta i's will be arbitrarily large. So that is another problem because, okay, so we have the same situation. Suppose we have fixed one separation line, and logistic regression is basically fitting inverse logit curve in this way. But actually, all observations here, all observation here is 0. And all observations here is 1. So that means logistic curve should be the very steep. So if we have the curve such as this, then basically the likelihood is higher. So each observation corresponds to this success probability. So anyway, so this area, so yellow group, if probability is closer to 0, higher. And for these red triangles, if the corresponding probability is higher, then likelihood is higher. So this is 1 and 0. So that means that this logistic curve, so logistic curve is represented by the probability is equal to 1, so e to the power eta over 1 plus e to the power eta. So in this situation, actually, the steeper curve, the steeper slope is better around here. So that means the beta goes to infinity. So actually, we cannot really estimate beta, and beta diverges to infinity. So we have to solve this question. And at first, before seeing remedies, we just try to fit this logistic regression. So first few lines, I described how to make the scatter plot in the previous figure. Then after that, we regress the logistic regression. And actually, if you fit this logistic regression, you got warning message that this algorithm did not converge. So this is expected because the beta hat goes to infinity. And this is the summary of the result. You can see, okay, so these numbers are pretty large. We are not exactly sure what's the appropriate numbers, but it's really large. And also, standard errors are really large. So Z value is very small. And so it causes the p-values very, least significant. So basically, we cannot get any reliable result. We don't have any significance in estimates. And also, you can see the null deviance and the residual deviance. We have a huge difference, even though we only have 2 parameters. So model is very significant, but we cannot really identify parameters, you can see. And actually, this does not converge after the several iterations. Probably this blows up, so the R stopped to calculate the estimates. R stops to update estimates. So in the next slide, next video, that we will discuss the method to fix this issue.